So a passive filter is a filter created using passive components like resistors, inductors, and capacitors. Just throwing an op-amp into the circuit does not automatically make it an active filter. Let me show you what I mean. So if I have a circuit here, then this is a passive filter over here. If I just take an op-amp, a non-inverting op-amp with gain, and I put it after a passive filter, this is not an active filter. This is just a passive filter followed by an op-amp with gain. In order to be an active filter, what we need to do is we need to provide some feedback from the output into the input so that it changes the filter characteristics from just the RLC networks. That's what makes it an active filter. Let's refresh our memory on the basic filter types. So this particular one, this is a low pass filter because it passes the low frequencies, but it attenuates the high frequencies. And we could implement a low pass filter with an RC network like so. So what will happen is at low frequency, the capacitor is an open circuit and you get the full magnitude out. But as we start to increase the frequency and the capacitor starts to turn into a short, well, then we will see a fall in the output. So we'll short the high frequencies out. This could be done with an RC network. You could also do the same thing with an RL network. So if you put the inductor here and the resistor here, at high frequencies, the inductor would be an open and you would get zero out, but at low frequencies, the inductor would be a short and you would get out what you're putting in. So you can implement a low pass or high pass filter with an RC or an RL filter. Typically it's done with capacitors because capacitors are lower cost. This drawing shows you the response of a high pass filter. So on the high frequencies, I get lots of output. So it's passing the high frequency, but at the low frequency, it drops off and I get to close to zero output. And that can be incorporated using R's and C's. So in order to make that, I want the high frequency to get to the output. So I would put the capacitor here and the resistor here. And here I would get a high pass filter response. Again, this is a passive filter. I have not used an active component to change its operation. Another thing you learned in AC, that if you picked the right values for the components, you could create a resonant circuit that actually generated a higher output at a certain frequency. How high it went depended on the ratio of the resistance to the LC components, and this was called damping factor. We can do the same thing in active circuits using op-amps with just capacitors. Section 19-5 talks about some active filters, specifically a VCVS filter, which is a voltage controlled voltage source. So you put a voltage in and you get a voltage out. So what I'm going to do is I'm going to first of all look at what happens if you put in a voltage without the feedback loop here. So let's say the feedback is open loop. Well, then you've basically got an RC filter here, which has a normal RC filter response, followed by a non-inverting amplifier, which has a gain of 1, and so you get out the filter response generated by this RC network. Now, when you add in a feedback capacitor, then what is happening is the signal here gets attenuated by the RC filter, and at this point here, you'll have a smaller voltage, which is out of phase from the original. That'll get reproduced on the output of the op-amp with the same magnitude and the same phase as what's going in on the positive terminal. And if it shorts out the capacitor, it means we've essentially added in a second source here onto the input, which is a smaller voltage. So as the frequency increases, this will keep the voltage on the output up a little bit longer. So instead of falling off with your typical RC response, what tends to happen is that the output voltage stays up longer because it's got some feedback, and then when it starts to fall off, it falls off faster. So this is how we create a second order response with a 40 dB per decade attenuation. So the cutoff frequency gets pushed out a little bit further, and then it starts to drop off quicker. So with one capacitor, we get something like that, and with the second capacitor in feedback mode, we get that. Let me show you in multisim how we can play with the value of these capacitors to get a different response. So here we are in multisim, and I'm going to try and give you some feel for how filters work with op amps. So here I have an RC filter. If I apply a voltage here, I would expect to see a reduced voltage here depending on frequency. And on the scope here, that's what we have. This is what's coming in. It's fairly big. And then what is coming out, which is the same as what's appearing on the non-inverting terminal, is a little bit phase shifted and a little bit attenuated. Now at the moment, the switch is open, so this scope shows us what's happening just in this filter. So since the output is fairly high and almost in phase with the input, when I close this switch, that should add into the input of the filter network, and it should make the output go up a little bit. So let's give that a shot. Let's run the simulation here, and that's what's happening now. And now I'm going to close the switch, and you can see as I close the switch, V out here went up just a little bit. Open, closed, open, closed. So the feedback through the capacitor increases the output a little bit at the cutoff frequency, which in this one is 4 kilohertz. If we look at the circuit response from the frequency perspective using the Bode plotter, we can see that the circuit has 0 dB. Over here in the low frequencies, its attenuation is 0 dB. This makes sense. We're getting out what we put in. But once we start to hit a certain frequency, it starts to drop off. It's down minus 3 dB at about 4 kilohertz. And then it continues to drop. So at this frequency, at 10 kilohertz, it's about minus 8. And at 100 kilohertz, it's about minus 28. So it's dropping at 20 dB per decade. Let's close this switch and run the simulation again. And now you can see that the drop off has really increased. And so now the cutoff frequency, again in here, this region, it's 0 dB, there's no loss. And we're down to minus 3 dB, which is now about 5 kilohertz. It used to be 4 kilohertz, so it's pushed the cutoff frequency out a little bit. It's held it off a little bit. And then once it starts dropping, so if I go to this point here, it's at minus 8 dB. And then I continue to go out to 10 times that frequency, and it's minus 44 dB. So now it's dropping at about 40 dB per decade. In the previous circuit, we built an active filter using capacitors in the input path and the feedback path that were the same value. I want to see what happens if I make them a different ratio. So here we have on the feedback path a capacitor that is 10 times bigger, and here we have one that is 1/10. So let's see what happens to the frequency response when I change the ratio of those capacitors. So currently we have 1:1, which is what we had before, and we have a minus 3 dB point at about 5K, and it rolls off at 40 dB per decade. So let's now change that to 20 nanofarads, and we'll restart the simulation. So now you can see that when the feedback capacitor is much bigger, it shorts sooner, and we get more feedback from the output back to the input, and it actually raises the output quite a bit here. So here we're actually 4.5 dB above what came in. So this is like a resonance circuit now, and we have a greater voltage at this peak value than we had that's actually coming in on the input. And then let's go to 1/10, stop simulation and restart. So now it's 1/10. So what is happening here is that takes a longer time, or it takes a higher frequency for that capacitor to cut in and make an impact. And you can see that for a good portion of the roll-off, it's rolling off at about 20 dB per decade. But then that capacitor starts to short out, and then it drops down to 40 dB per decade down in this region here. So this is what happens when you play with different values of these capacitors. Let's see what happens when we play with gain. What happens when we increase this capacitor 10 times is that we reduce XC to 1/10 of its previous value. This means that more of the feedback signal will add into what's coming in, and that's the reason we get this little peak here at lower frequencies when we make this capacitor bigger. So if I made this 20 nanofarads or 200 nanofarads, then this would get bigger and it would happen at a lower frequency. Note that the concept there is that I'm making the output bigger and adding it to the input. And there's another way to make the output bigger, and that's to turn this op-amp into a non-inverting op-amp with gain. So here I've done that. I've added a couple of gain resistors here. If I'm in this position, then this goes straight back to there, and the gain is 1. It's a voltage follower. If I go to this position here, it's now gain of 1.5. This is 2, and this is 3. So let's see what happens. So I'm going to restart the simulation. And here you can see with the voltage follower, I've got the cutoff frequency at probably about 5 kilohertz. It's minus 3 dB down, and it's 40 dB per decade. Now I'm going to increase that gain a little bit and start over, and we should see a little bit of a shift in the output. So the output went up a little bit because the gain is now 1.5. So this should be up a couple dB, and it is. It's now 3 dB instead of 0. But it also made this corner a little bit squarer. So now let's go to gain of 2. So with gain of 2, now you can see that the output went up a little bit across the range, but you can also see we're actually starting to get a bigger output than what's coming in, and we're starting to see a resonant frequency in here. Now let's go to 3 times. So this is a gain of 3 times. And we restart the simulation, and now you can see the nominal gain is about 3 times bigger, but at the resonant frequency that's created, we can see a big spike. In fact, if I make this like 60 dB, you can see that the output rises like 60 dB, which is a significant increase. And there's a problem with having an output that peaks so much here, because if there's any kind of a little bit of an oscillation here, then what can happen? It can start to oscillate at this frequency, and it doesn't matter what the input is. Basically, the output becomes so large that it overpowers the input, and the only thing you see is a frequency out at this value here. So by playing with the gain factors, we can also modify the characteristics of the low-pass filter. Now, I've been trying to give you a more intuitive feel for how filters work, and how we can use an active filter to generate a second order response. But you may be asking yourself, how do I figure out an exact voltage out given a voltage in at a certain frequency? And that can be rather difficult. The first thing you'd have to do is you'd have to figure out the magnitude of the XC at the frequency of interest and the phase angle, and you'd have to replace your power supply here with a dependent circuit, which has an output which is something times V in, and that will be your output voltage. And it would be a rather complex problem to figure this out for all frequencies, enough to draw a Bode plot response. So in general, we don't solve these for values. Now you could also use Laplace transforms and work on this problem in the S domain. And you're going to learn how to do that in your advanced calculus course. But the reality is that in order to find or design these filter circuits, what ends up happening is that there's a cookbook of known good circuits that you can start with, and you would put them into a simulation package like Multisim, and you would tweak its values. Now, there isn't going to be every circuit in there. Let's say this one here, where you have equal value components of R and C. This is called an equal value voltage controlled voltage source. And those types of circuits will be in cookbooks, and they'll have ready-made formulas for you. So you can start with those and then modify it from there to get the filter that you desire.